Today we will continue with hypothesis testing on population proportion, and that's 10.2, and hypothesis testing on population variance or standard deviation from 10.4. We did 10.3 last time on Monday, and again, even that one relies heavily on you have watched the lecture video. Okay, now once you are done with 10.3, then you can go on to 10.2. The template will be the same. Number one, the claim. Second, hypothesis. Third, test statistic. Fourth, test p-value. Fifth, informal conclusion. Sixth, conclusion. And just like last time, every time I'm done with all these 6 steps, I inserted how to compute the critical value, which is all of them are the same to what we have done before with some variation. Now, in the past, on Monday, we did hypothesis testing on population mean. So that this part here was mu. Right now, we are testing the p. So we changed that to p. Okay. On Monday, the test statistic was C-score. If we know, let me write it down. Was null hypothesis mu equals to less than equals to greater equals to a number. Alternate hypothesis was mu not equal to greater than less than a number. Okay, and then the test statistic we use C if sigma is known. We use T if sigma is unknown. Right. Oh yeah, at that time, we can use this procedure if the underlying population, the population from which the sample obtained is normally distributed, or the sample size is at least 30. Okay, that was the requirement. Now, for population proportion, the requirement is that n times p hat times q hat is at least 10. Okay, but we don't really. I will show you later on when how to say that. Basically, the sample size has to be big enough. Yeah, the sample size has to be big enough. You will see that the sample size has to be at least 40 actually. Okay, more than 40. Okay, now in the past, the requirement was so you see that statistic changes, right? Due to the advancement of technology. Now in the past, the number of successes should be more than 5, and the number of failure also more at least 5. Now, right now, the current one is basically the number of successes, which is n times p hat, times q hat has to be at least 10. Okay, that's what they say. Now, so Thomas, which one you use? In practice, people still follow the past one. So you look at the number of successes and number of failures. If both of them at least 5, then go ahead, use this. Okay, but if you want to be strict with the statistic, with the more recent one, then we follow the current requirement. Okay, but the procedure, the template basically are the same. Okay, now let's start. Just like before, instead of starting from the word problems, we will see the technicality first. Okay, now I will do number 7 and maybe with number 11 here. They don't give us the claim for this number 7 to number 11. So because we don't have the claim, we will not have step 6 either. Okay, now let me start. Number 7. The claim, none. Step 2, provided to us, hypothesis. Null hypothesis is P equals to 0.3. The alternate hypothesis, P is greater than 0.3. So from here we see, because P is greater than, then this must be a right tail. Okay. Step 3 is test statistic. That will be Z equals to P hat. Now let's compute what is the P hat first. P hat is X over N, which is, in this case, 75 over 200. That's 0.375, right? Okay, therefore, Q hat will be 1 minus that. That's 0.625. That's for Q hat. Now, if we want to compute the requirement, right? The requirement, does this satisfy the requirement? N times P hat times Q hat. Now, N times P is the number of successes, X, multiplied by Q hat. Okay, 75 times 0.625. Is it more than 10? You can see it's more than 10 already. So we can use this procedure. Okay, so we can use this procedure. C equals to P hat 0.375 minus P, the parameter. Okay, P, the parameter. Now, of course, just like before, the parameter always comes from the constant from the null hypothesis. Okay, always comes from the constant from the null hypothesis. Okay. Divided by square root of 0.375. I'm sorry, no, that's not right. 0.3, that's the P. Okay, times 0.7, that's the Q, over the sample size 200. Okay, go back. Let's see. See, the formula here is PQ inside the square root on the denominator. Okay, so the Q is 1 minus P, that will be 0.7. Now then you can use your calculator. Use our calculator. 0.375 minus 0.3. Now the whole, after you know what, I show you my calculator. So I have 0.375 minus 0.3. That's the numerator, right? Now then, divide that by the square root of, it's already inside the square root, 0.3 times 0.7 divided by 200. Now notice that 0.3 times 0.7 divided by 200 are all inside the square root, which is on the denominator. So I get 2.31455. 2.31455. Now then, step 4. Step 4, the p-value. What is the p-value? We look at the standard normal distribution. The test statistic is 2.31455. It's right tail, so I need to find the area here. The p-value will be normal CDF 2.31455 E9901. You use your calculator. Let me change to regular view. 2.31455. I get this is 0.010318, rounded to 2, 5 decimal places. Now then, step 5. Let's see, the alpha is 5%, which is greater than my p-value. Okay, so the informal conclusion will be reject null hypothesis. Okay, because the p-value is smaller than alpha. And the same rule we have before. Okay, and then step 6, the conclusion. We cannot draw any conclusion because we don't even have a claim. Okay, now how about the critical value? Step 4B, critical value. Now we start with the standard normal distribution. We need alpha 5% on the right tail. So I need to find out what is the critical value here such that the area to the right is 5%. Okay, now if the area to the right is 5%, then the area to the left is 95%. So C critical is inverse norm 0.9501, which I believe is 1.64485. Let me make sure. That's right. So that's the critical value, 1.644 something, while the test statistic is greater than that, right? It's in the tail. So once it is in the tail, this is a test statistic, which is the 2.31 something, right? Okay, now because the test statistic is in the tail, then we reject null hypothesis. So using p-value method or critical value method, the conclusion always the same. Okay, now let's try number 11. Now after number 11, then we attack word problems. Number 11, The claim is none, they don't give it to us. Oh, you know what? Let's check first if it is actually possible for us to use this model. Okay, let's check. So you see that the n is 500, the x is 440. So p hat is 440 over 500. That's 0.88. Now q hat therefore will be 1 minus 0.88. That's 0.12. Now then what is n times p hat times q hat? That's the same to x times q hat. That's 440 multiplied by 0.12. That's more than 10 for sure. That's 40 something, maybe even 50. Okay, so we can now use this model. Okay, that's just a little check though. That's just little check. Do you need to show the check in my test? No, no need. No need. Okay, in my test, just go ahead with the hypothesis testing. Because if what happened if MP hat Q hat is less than 10, then you cannot do anything, right? Okay, what's the point of me asking that question? So I will give you a question that you can assume that we can, every time I ask you hypothesis testing for proportion, population proportion, you can always use that, this procedure. Okay, step 2, hypothesis. Null hypothesis, P equals to 0.9. Alternate hypothesis, P is not equals to 0.9. Now, because it says not equals to, it can be more than 0.9, can be less than 0.9, then we know it is two-tailed. We know it is two-tailed. What happened? I want to get the red color. That's a two-tailed. Okay, now then step 3, how about the test statistic? Z equals to P hat, which is 0.88, minus P, which is 0.9, over square root of P, which is 0.9, times Q, which is 0.1, over sample size 500. Okay. Which is equal to, now make sure you use your calculator to check together with me. Hold on. I get a very strange. Oh, I see. I think I typed something wrong. I'm sorry. Yeah, this is supposed to be negative 0.47140. That's the test statistic. Now, step 4. What is the p-value? The p-value is the area of the tail from the test statistic to more extreme. Now in this case, because it's a two-tail, whatever that area, I will need to double it. Okay, I need to double it. So p-value is equals to 2 times normal CDF negative E99 negative 0.47140 0, 1. Then use your calculator. So it is impossible for you to be able to go on with this course if you still don't have your calculator, though. You need to have your calculator. Okay, this is already week number 13. Okay, you need to have calculator or at least get the emulator, the one that works with your computer. This is times 2, I get 0.63736. Oh, that's very, very big. So we will fail to reject null hypothesis because the p-value is greater than. Okay, informal conclusion. Fail to reject null hypothesis. Again, conclusion, because we don't have the claim, we cannot draw any conclusion. Okay, now I hope it is that simple. Now, before I go on, let me show you how to use calculator to confirm your answer. Now, calculator use is not to replace, the calculator use is not to replace the structure, the calculator, only to help you computing to confirm what we have. Now, let's see number 11. We have n is 500 and x is 440, right? Now, if we want to use calculator, so calculator use, calculator use is only to confirm your answer, but not to substitute your work. I require that to be done in these 6 steps. Okay. Now, if you use calculator, what do you need to do? You will go to stat and then go to test. And then you go to one prop z test, one proportion z test. Okay. Actually, when it comes to proportion, it's always C test, C standard normal distribution test. Okay. Now let me show you. You go to stat, test, one prop C test. Then they will ask you what is the P naught. What is the P naught here is whatever you see in the null hypothesis. In this case, is 0.9. Okay. In this case, is 0.9. Let me see again. This is the information here. Okay, the X is 440. That's the number of successes. N is 500. That's sample size. Okay, and you want to check against not equal. Now, this is from your alternate hypothesis. Okay, and then calculate. This is what we get. Let me screenshot that and put it at here. Put that here. Hold on. Why do I get a different number? Give me a second. Yeah, why do I get different number? My C-score is different. My C-score is different. Let me check. Maybe I typed something wrong. Yeah, maybe I typed something wrong. Yeah, you see that my C-score is 0.47 something, but their C-score is negative 1.49 something. Yeah, let me check again. Okay, so it's 0.88 minus 0.9 divided by square root of 0.9 times 0.1 divided by 500. Oh, yeah, I typed something wrong earlier, I guess. Okay, so this is negative 1.49071. Okay, I need to change this. Negative 1.49071. Okay, so that will be normal, normal CDF. Lower bound negative E99, upper bound is negative 1.49071. The mean is 0, standard deviation is 1. 0.06802, 0.06802. Right? And then multiply that by 2, 0.13604. 0.13604. Well, I still reject null hypothesis, but the number was incorrect earlier. Yeah, good thing I checked that, otherwise I will not know. Okay, now let's check again the one I had earlier here. For number 7. For number 7, let me move it here. Okay, go to stat, test, one proportion C test. The P naught is 0.3. Number of successes 75. Sample size 200. And then I will check greater than, oh, actually less than P naught. Less than P naught. That's oh, greater than P naught. Yeah, greater than 0.3. Right? That's what we get. Let me screenshot that. I just don't know where to put it though. Let me put it here. I think I need to make the size very, very small. Okay, so let's see. So you see the C-score, the C-score we have here, 2.31455, 2.31455. Okay, and then our p-value is 0.013 something. That's our p-value. Okay, now this one is p-hat. This one is p-hat. That's our p-hat. Okay, yeah, that's how we check that. If you want to see how we check our previous work, the one from the 10th, let me see this one here. Okay. For example, how do we check hypothesis testing with on mu with sigma known? Okay, you know what? Let me go back here. Let me go back here. Okay, do this, the new page. So extra to confirm your hypothesis testing on mu. If sigma is known, then you will use go to stat and then test and then use z-test. Okay, if sigma is unknown, then you will use stat, test, t-test. Okay, now, for example, if we look back to what we did on Monday, let's say hypothesis testing on mu with sigma known. Hypothesis testing on mu with sigma known number 15. Number 15. So I go to stat, test, sigma known, right? So we will use z-test. Now the input, we use statistic because they give us the x bar and sigma. Okay, stats. Then what is the claim mu? Okay, you read that again. Okay, but the claim for the mu is 9.02. Population standard deviation 0.7. Sample mean 8.1. Sample size is 12. And we are checking for less than the claim mu, which is 9.02. That's what we get. Let me screenshot this first. And compare it here. Compare it here. I want to come here. Yeah, let me put it here. You see, my test statistic here, negative 4.55282, right? By rounding. And our p-value is 2.649 something e to the negative 6, right? Okay. But of course, when you write it, you need to write it this way. Okay. Where the 2 here, this 2 here, starts at the 6th decimal place. Okay. Now let me move this there. So instead of putting it here, let me move it to our notes today. This is for number 15 from section 10.2. If sigma instead is, I forgot, is it 0.7? Look at my note, not this one, sorry, wrong page. Yeah, 0.7, with sigma 0.7. So at that time, we assume the sigma is known. Now, what happens if we redo number 15 from that section 10.2? Instead, we keep that S equals to 0.7. Sample standard deviation is 0.7. So when I use calculator, I cannot use z-test. I cannot use z-test. I will use t-test. Okay, t-test. All the information here are the same. Okay, sample standard deviation 0.7. Is this one less than? Calculate. So this is what we get. What am I doing? This is what we get. Okay, let's compare it to what we had at that time. For number 15. Number 15, let me put it here. So you see our test statistic is the same. Our p value is this, right? So using calculator, it will give you only the test statistic and p value. Okay, but it doesn't give you step 1, step 2, step 3. I mean 1, 2, 5, 6. No, they don't do it for you. Okay. Now let's go back to what we do today. This time, then we will start working on word problems. Let me pick questions from our textbook. Let me use number 17. I try not to pick questions that has a long wording. Yeah, I don't want to have you like spend more time reading the question than working on the problem. Okay, number 17. The drug Lipitor is meant to reduce cholesterol and LDL cholesterol. In clinical trials, 19 out of 863. So the X is 19, the N is 863. So 19 out of 863 patients taking 10 milligrams of Lipitor daily complain of flu-like symptoms. Suppose that it is known that 1.9% of patients taking competing drugs complain of flu-like symptoms. So that's the P that they are comparing. That's 1.9%. Is there evidence to conclude that more than 1.9% of Lipitor users experience flu-like symptoms as a side effect? Now, at alpha equals to 0.01. Okay, let's start step 1, claim. The claim is, just take it from the questions. Like sometimes it's explicit, sometimes it is implicit. Now here, is there evidence to conclude that? That's where your claim start, right? More than 1.9% of Lipitor users experience flu-like symptoms as side effect. That's our claim. Okay, more than 1.9% of Lipitor users experience flu-like symptoms as a side effect. Okay, here's the thing. We want to see if Lipitor actually cause this side effect, the flu-like symptoms. Now, you cannot say because 19 of them have this flu-like symptoms, then it must be because of Lipitor. Okay, who knows that if you get a random 863 patients, you get even more people with flu-like symptoms. Then it actually implies Lipitor reduced that, right? Okay. In other words, can we use how to say that, direct the accusation of flu-like symptoms is caused by Lipitor in this case, right? Simply because some of them experience flu-like doesn't mean it's because of the drug, right? It is possible that those people already have it, okay, and it has nothing to do with this Lipitor. Okay, now think of that as the case that we have a lot in our surrounding regarding COVID-19. Okay, it's like in the past, this is what people say. Okay, in the past, the way United States, by the way, United States count COVID death. Okay, the way that we count COVID death is if a death involves COVID. In other words, let's say Thomas suddenly died, and he happens to have COVID-19 at that time at the time of his passing, then it is counted as COVID death. Now, this way of counting is not the same country to country. Okay, in America, that's what happened. Now, in other country, let's say other country, I don't want to say their country, okay? If a death is caused by nothing else, but COVID, then it is counted as a COVID death. Okay, so imagine Thomas happened to have a COVID, stay at home, okay, and for some strange reason, oh, you know what, I have emergency, I have to go out, I have to do something, I have to buy something, and on my way to that place, I get hit, okay, I have an accident and I die, okay. In that country, it will not be counted as a COVID death. Why? Because the cause of death is actually by accident, car accident, not because of COVID. But in the United States, it will be counted as COVID death. Okay, of course, not in that extreme case, but I'm trying to say is like, suppose I already have asthma. Okay, I already have asthma. And the reason I die is actually because of my asthma, which happened to be at the same time I have COVID. Okay, will that be counted as COVID death? In America, it is yes. In other country, maybe not. Okay, now for some strange reason, US flu last year goes down very, very low, as if no more flu in United States, but it is all replaced by COVID-19. Okay, why? Because of this kind of counting. Okay, now I'm not here to say that US way of counting the COVID death is wrong. No, I'm just saying that this is different way to look at that. Okay, who knows? America is actually writing them for now as COVID deaths, and they will review that again further. Okay, and say, oh, this is really caused by COVID. Oh, that one is not. Okay, each way of counting method are not perfect. Okay, each one of them not perfect. But of course, because the number for US death is actually counted this way, then you will see that US death is US COVID death at this point, especially last year. Okay, I know it's quite political, was actually inflated. Okay, there are some deaths which was not caused by COVID simply because that person happened to have COVID, but was actually okay, suddenly counted as COVID death. Okay, now going back here. If somebody have flu-like symptoms and that person happened to take Lipitor, will you assign the flu-like symptoms to be caused by that Lipitor? Or is it just simply happen to be something that that person also have and has nothing to do with Lipitor? Okay, so you see, even though this question is on Lipitor, the application is actually far-reaching. Okay, in the past, we also applied this for example, is cell phone cause brain or nerve cancer? Okay, let's say I make up numbers. Let's say they found out that 0.1% of cell phone users experience and contracted or then have brain cancer. Okay, will you say it's because of simply because you find this out from those cancer use from those cell phone users, then you blame it on cell phone? No. What happened if of those people who don't use cell phone, we found out that 0.5% of them actually have brain cancer? Will you then say that cell phones actually reduce brain cancer? Will you say that? No, you will not say it that way. Okay, then you should not even say that cell phone cause brain cancer, because even if those people don't use cell phones, they have even higher brain cancer case incidence. Does it make sense? Okay, so that's why we do this hypothesis testing. Okay, is it really caused by Lipitor, or it's already something happens by coincidence? Or can we even say, in case this 1.9 is, in case this 19 over 800 something is actually less than, if it is actually less than 1.9, can we say that Lipitor reduce flu-like symptoms, like which is not the our intention? Okay. Now, this is just an example, but through this example, we see how we actually use, when do we use this hypothesis testing to check somebody's claim. Okay, it's simply because we have 19 out of 863 patients have who take Lipitor suffer from flu-like symptoms. Does it mean it is caused by Lipitor? Okay, then we're supposed to do this hypothesis testing. Now, students who have not been exposed to hypothesis testing that we are doing here, they may blame it on Lipitor right away by just reading it. Oh, it must be because of Lipitor. Why? Because these 19 people, 19 of them actually, they took Lipitor. No, it is possible that they happen to be just working at night and happen to be raining and they caught some rain at night. Who knows, right? Okay, so step 2, hypothesis. The purpose of we keep the structure like this 1, 2, 3, 4, 5, 6 is to make sure that we are so tight, so strict, that the conclusion we get is supported by evidence and not by some lie. Okay, now we want to know if the P, the proportion of people taking Lipitor and have flu-like symptoms is more than 1.9%. So the alternate hypothesis P is greater than, right? More than, from the word more than. greater than, right? 1.9%. Okay, so this P here is less than equals to 1.9%. Just like what I said on Monday, our textbook will use, just like a lot of other textbook will use, P equals to 1.9%. Okay. Anyway, from the alternate hypothesis we see, then this will be a right tail test. Why? Because we need to show that the proportion of people suffering from flu-like symptoms, knowing they take Lipitor, is much higher than 1.9, not just barely a little bit higher than 1.9, which can happen by random chance. Okay. Now then, test statistic. Z is equal to, what is my p hat? Let me do it here. P hat is 19 over 863. Nineteen over 863. I get 0.022016. Therefore, what is my, if my P here is 1.9%, then my Q will be 1 minus 0.019. That is 0.981. Okay, now then the C score will be 0.02202 minus 0.019 big over square root of 0.019 times 0.981 P times Q. Okay, over sample size 863. Okay, then we will use our calculator to compute this 0.02202 minus 0.019 divided by the square root of 0.019 times 0.981 divided by 863. I get positive 0.64983. That's my test statistic. Therefore, what is my p-value? My p-value, we have standard normal distribution. Test statistic is 0.64983. The p-value is this area here, right? So p-value is normal CDF 0.64983 E9901. I get 0.25790. Now then, let me continue my step 5 here. Oh, no. Let me not do it. I want to save some space for my my 4B. Step 5. Let me do it here. Informal conclusion. My alpha is 0.01. Okay, so fail to reject null hypothesis. Okay, and step 6, what is the conclusion? Now we want to conclude that more than, that's the claim, right? We want to conclude that more than 1.9% of Lipitor users experience flu-like symptoms as a side effect. Now the thing is, the evidence does not show that. Okay, the evidence does not support that. So we will say at 1% significance level, there is insufficient evidence to support the claim that, now copy paste whatever you have in your claim, okay, that more than 1.9% of Lipitor users experience flu-like symptoms as a side effect. Okay. Now next, what if I want to show the critical value? So let me do the 4B here, critical value. So you see that from test statistic, you can get the critical value and you compare that with the alpha. I'm sorry, from test statistic, you find the p-value, not critical value. From test statistic, you get the p-value and compare that to alpha. Or you can use significance level to find the critical value and compare that to test statistic. Okay, test statistic give you p-value, then compare to alpha. Or using alpha, you get critical value and compare to test statistic. You see? Okay, this is the p-value method. This is the critical value method. Okay, p-value method is this one. Critical value method is this one. Okay. Now then it's right tail, so it's here. We need to find this critical value such that the area to the right is equal to alpha, which is 1%. And the area to the left, therefore, is 99%, right? Okay, so C critical is inverse norm 0.9901. We will get 2.32 635. Now notice that our test statistic is here. This is our test statistic, which is not on the tail. Okay, now if you want to have extra 1 point, that's what you want to show me. Show me the critical value. Okay, now how about if we use calculator? Let me use calculator. Go to stats, test, 1 proportion C test. Okay, the constant we use in the null hypothesis, that's 0.019. The sample of the Number of incidences 19 of 863 people. And we are testing right tail. Okay, let me screenshot and put it on our note. Now, again, this is only to confirm what we have. Okay, this is only to confirm what we have. The p-value is this. A bit off, huh? How about our c-score? Our c-score is this. A bit off. I wonder why it's always a bit off. Did I type anything wrong or what? You know what? I'm not happy with this. My p-hat is correct though. Oh, I think I know. I think I know why. I think I know why. This little rounding error here may affect the number. Yeah. Yeah, that little rounding error. That may affect the number. Yeah, it's supposed to be 0.16, right? Okay, but you see the p-value is actually not much different. Okay, let's show the computation more precisely. Okay, so I will start with this. My p-hat is 19 over 863. That's the p-hat supposed to be. And then I subtract by 0.019. So this number is not rounded at all. Okay, divided by square root of 0.019 times 0.981 divided by 863. I'm supposed to get the same number they have there. Yeah, you see? I'm supposed to get the same number it has here. It is caused because of my rounding error. Okay, I round the fifth decimal place. I round the fifth decimal place by just a little bit, but it affects so much. Yeah, it affects so much. So do not underestimate what when I say, well, you know what, round it to only round it to 5 decimal places. Okay, even though we still come up with the same conclusion, but if you round to like around 2 decimal places, the error will be a lot larger. Okay. Oh shoot, I didn't show you what I have earlier. Okay, this is what I wanted to show you earlier. I'm sorry. This is what I want to show you earlier. This is what I did, 19 over 863. This is the number. Notice that I round this to 0.2, 5 decimal places, right? But because of that rounding, notice that my test statistic that's supposed to be, okay, 0.649, 0.649, okay to 3 decimal places, but the fourth decimal place is already very different. Okay, because of that little rounding error. So the little rounding error we made earlier is actually a very big effect, especially in this 10.2. Okay, now the p-value, as you can see, the p-value because of that, we are off by, let me write them next to each other. So the correct one is 0.25816. So you see, already off by on the 4th and 5th decimal place. So how do I know which one is the correct one, Thomas? Just use the computation you have by hand and your calculator only to confirm. Okay. Now, but you do not want to expect that because you do some rounding, and your result will be exactly the same too if you don't do any rounding. Okay, I did rounding here. And the fact is I have a little bit off here. I have a little bit off here. Okay, but not too much though, not too much. Not too much error. Okay, we still come up with the same conclusion, but especially we are close to, if we round to 3 decimal places, we are the same. Okay, now let's do one more problem from here, from this section. I hope they are good enough. Let me do number how about number 23. Number 23 in our textbook, quality of education. In August 2002, 47% of parents with children in K to 12, hold on, let me copy, paste the rest. From K to 12, were satisfied with the quality of education of the student received, 47%. Now that's in 2002. Now a recent Gallup poll found that 437 of 1,013 parents, this is not in 2002 anymore, with children in grades K to 12 were satisfied. So the N is 1,013. The X is 437. Okay. Now, I don't teach you how to use confidence interval. I will not teach you to use confidence interval. Okay. We will still use hypothesis testing. Okay. We will still use hypothesis testing method, the traditional or p-value method, to come up with the conclusion. Now, let's just decide that because of that 95%, so let's use alpha equals to 0.05, which is 5%. Okay, construct or do hypothesis testing to assess whether this represents evidence that parents' attitude toward quality of education has changed. Has changed. That's the claim. Claim. Okay. Parents' attitude toward the quality of education in the United States has changed since August 2002. Has changed. So maybe increasing, maybe decreasing. It doesn't say going down, doesn't say going up, it just say change. So the hypothesis will be that the proportion of parents' attitude is no longer 47% satisfied. Okay, the null hypothesis will be P still equal to 0.47. Now from the sign of the alternate hypothesis not equal to, we know that this is a two-tailed test, which means later on, when we compute the p-value, we need to double it. Step 3, test statistic. I need to first compute what is the p-hat. From here, we get the p-hat to be 437 over 1013. I will still round it to 5 decimal places. Okay, but I know that because I do that little rounding, even I round to 5 decimal places, I have the risk of having different test statistic up to 3 decimal places. Okay, 437 divided by 1013, I get 0.43139. So the test statistic will be, oh, you know what? Let me put a mark here that we'll use alpha equals to 0.05 instead. Okay, so this will be 0.43139 minus 0.47. That's the P in the null hypothesis over square root of 0.47 times 0.53. That's the Q. That's the Q. Over the sample size, which is 1013. The number I get is negative 2.46205. Then step 4, p-value. The test statistic is negative 2.46205, but it is two-tailed. So later on, I need to double it, not only the area there, but also the area to the right. P-value equals to 2 times normal CDF, negative E99, negative 2.64620501 for standard normal distribution. I get 0.00691. When I multiply it by 2, I get 0.01381, which is less than alpha, So my step 5 will be informal conclusion, reject null hypothesis. Now, if we reject null hypothesis, then the conclusion will be that we have enough evidence. At 5% significance level, there is the evidence support, I will just say the evidence support the claim. The evidence support the claim that. So the wording for conclusion is not only the sample data supports or there's enough evidence to support, there is sufficient evidence to support, the evidence support the claim that. Okay. that parents' attitudes, but after the claim that, you need to copy paste whatever you said in your claim. What you don't want to happen, they claim one thing but conclude another thing. It's like they claim, for example, Thomas is a very bad teacher, so the conclusion is you need to take Mr. A teacher. No, that's not the conclusion. Okay, you did hypothesis testing on Thomas a good teacher or not, for example, right? So the conclusion should be Thomas is a good teacher. The evidence support the claim that Thomas is a good teacher, or the evidence does not support the claim that Thomas is a bad teacher, or so on and so forth, right? It has nothing to do with Mr. A or Mr. B. Okay, your claim and your testing all directed toward Thomas. Why all of a sudden you direct later on, then you need to take class with somebody else? Okay. If Thomas is a bad teacher, your conclusion is basically that there's enough evidence to support Thomas is a bad teacher. Conclusion, don't take Thomas class. Okay, but does it mean you take another teacher's class? Well, then you need to do hypothesis testing on that teacher. Okay. I hope it makes sense for you. Okay. And now what usually happen is that, though. What usually happen is that, okay, well, they claim one thing, they conclude another thing. Just like our last presidential election, okay? We say bad thing about Mr. A, so you need to elect Mr. B. Well, no, you do hypothesis testing on Mr. A, it just simply means Mr. A is bad. To know that I should elect Mr. B instead, I need to do hypothesis testing on Mr. B. Okay, if you want to compare A and B, then do hypothesis testing appropriate to that. That's in chapter 11. That's not in chapter 10. Okay. But that's what usually happen though. People claim one thing, especially with our mass media right now. They claim one thing, but they conclude another thing. It's like, what? Okay, that's why when you conclude, you need to say if the evidence support or does not support the claim, and you need to say the claim again as what is mentioned in step 1. Okay, the parents' attitudes toward the quality of education in the US has changed since August 2002. Now notice that the claim was talking about parents' attitudes. It doesn't say anything about the quality of education already decreased or not. Okay, parents' attitudes now being judged. We are not judging the quality of education. Okay, we are judging their attitudes. Okay, their attitude already changed. Does it mean the quality already changed? We don't know. Okay, but I don't think, of course, we all agree that we do not judge the quality of education or a lot of other things based on people's opinion. Okay, like the best way, in my opinion, to judge if I'm a good teacher or not is see if you can apply what I teach you in your next class, in your life, instead of just seeing that, oh, you know what, students say this, say that about me, you know, even though I think about that too, you know, I will consider that. But it doesn't mean if students say A, I will listen and I need to be A. No, after all, I'm your teacher, you right? I'm your teacher. You're supposed to be the one listen to me, not me listen to you. Okay. Now I'm saying this because one day you will be parents too, right? Okay, or maybe you are already parents. If you are parents, then you listen to your children, or your children supposed to listen to you. Which direction it goes? Okay, I have children too. Do I listen to them at times? I need to be able to filter out what is the quote unquote the noise, what I need to listen and understand. Okay, and what other things that, hey, you know what? Welcome to life. There's something called discipline and education. Okay, because at home I teach my children to keep a good manner, behavior. Okay, I know they are children, they still do silly things, but every time they do so, I have to let them know. I cannot say, well, it's okay, every children's doing that, so I should just let it go. No, that's not how we work. Critical values, 4 extra credit, right? Okay. Now the alpha is 0.05, but it's two-tailed, so it's 2.5% each tail. We have 2 critical values, so critical values will be plus minus normal CDF. I'm sorry, it should be inverse norm. Inverse norm. This will be 95% in the middle, so 0.97501. That will be plus minus 1.9695996. I happen to memorize the number. Okay, and you can see the test statistic, negative 2.46 is actually here. Right? It's on the tail region. So we reject null hypothesis. Okay, our last part, just to confirm, right? Just to confirm, if I want to confirm if I get the same result, stat test, one proportion test, the P naught is 0.47. The X is, oh, I need to see my notes here. X is 437 out of 1013. And we test against two-tail. Calculate. That's the screenshot. Again, in my test, you don't need to do this. You don't need to screenshot your calculator. No, that's only for your personal use. Okay, if you want to see, did I do it right? Just to make sure, you know. Okay, and you see that the p-value is actually the same. Our test statistic also the same. Okay, now that's for this 10.2. Suggested homework from here. Let me ask you to do question number, from number 7 to number 21. From number suggested homework from this 10.2, number 7 to number 21. And if you see the question is really long, just skip that question. Okay, focus on this structure 1, 2, 3, 4, 5, 6, and to get the critical value, and to check using your calculator. Okay, let's take a break, and then when we come back, we will do 10.4, which is hypothesis testing on population variance or population standard deviation. You know what? Let's at least give us the template first. We work on the template first. Hypothesis testing on population variance, which is sigma squared, or population standard deviation, sigma. The template, the same, always 6 steps. Step 1, the claim. Step 2, hypothesis. Is null hypothesis, alternate hypothesis, sigma squared. That's what we are testing, is equal to or not equal to. Less than, equal to, or greater than. Greater than, equals to, or less than a constant. Or if you are testing standard deviation instead, then instead of sigma squared, it will be sigma. Okay? If in the claim, it's standard deviation instead. Now, step 3, how about the test statistic? We will use chi-squared. Chi-squared equals to degree of freedom, n minus 1, times sample variance over population variance. Okay, the population variance is later on coming from here. Then from there, we do p-value. Don't forget chi-squared distribution is positive, skewed to the right, continuous distribution. That's what it looks like. Okay, now to compute p-value, depends on which tail you use. Like if 2 tail, then you multiply by 2. But the function we use later on will be chi-squared CDF. On your calculator, it's usually right below TCDF. Yeah, below T distribution, you will see chi-squared distribution. Okay. We will have, after that, it's informal conclusion. With the same rule, reject or fail to reject null hypothesis, and then with conclusion. Okay, the only new stuff are here in step 2 and step 3, and of course step 4. Okay, but step 1, step 5, step 6, the same rule. Step 1, the claim from the questions. Informal conclusion, compare that with the alpha. Okay, now for critical value later on, we need to find the chi-squared critical, right? Then we will use inverse chi. Okay, which we programmed to our calculator last week before the test on, last week, or maybe even longer than that. Okay, now we'll take a break. We come back at 5. Let's say we come back at 5:45. Right now it's 5:31. We come back at 5:45. Okay, let's continue. We will do problems from this 10.4. Let's take a look. Let's do question number 1 first. Finding the critical values. They are A, B, C. Oh, I want to erase this. So number 1A, determine the critical value for right-tail test of a population standard deviation with 18 degrees of freedom. So the degrees freedom is 18 and alpha equals to 0.05. Let's see. So number 1A, let's sketch the chi-square distribution. Okay, it's a right tail. So the area of the tail on the right-hand side should be 5%. Okay, we want to find this chi-square critical. It will be inverse chi area to the right, 0. For chi-square, the area is to the right, and degree freedom 18. Okay, and you use your calculator. Inverse chi, we use program, right? Inverse chi. And then area to the right, 0.05, degree of freedom 18, 28.8699, actually 86930. 28.86930. That's for number 1A. Number 1B, let me do it here. Determine the critical value for left tail with sample size 23. Left tail alpha is 10%. The area here is 10%, 0.1. Okay, and the sample size is 23, which means degree of freedom is 22. Right? Okay, so this chi-square critical is inverse chi. The area to the right is 0.9. Okay, remember, inverse chi is different from that inverse t or inverse norm, where those are area to the left. Inverse chi is area to the right. Degree of freedom 22. So inverse chi, area to the right 0.9, degree of freedom 22. 14.04149. 14.04149. Okay, and then 1C, determine the critical values for two-tail test. Oh, two-tail test. So we will have two critical values here. Okay, the level of significance alpha is 5%. Because it's two-tailed, then the area for each will be 2.5%. 0.025 here. This is 0.025 here. Okay, let's call this chi-square critical right. And this is chi-square critical left. Now, chi-squared critical right will be inverse chi, area to the right 0.025. Degree of freedom, the n is 30. So the degree of freedom is 29. Okay. And later on, chi-squared critical left will be inverse chi. Area to the left is 0.025, therefore area to the right is 0.975, degree of freedom 29. So inverse chi 0.025, degree of freedom 29. 45.72229. 45.72285. Let me call that 9. And for chi-squared critical left, area to the right 0.975, degree of freedom 29. It's 16.04707. 16.04707. Now that's for the critical value. Okay, if you need to use critical value method, well, that's good for extra 1 point, right? Okay, now let's see more. Let's see number 3 maybe. Or should I go to number 7? Why not? Number 7 is right in front of me. Beside number 3, number 7. They give us the hypothesis. Okay, the sample size is 12. Now remember, for us to apply this hypothesis testing, the population has to be from normally distributed population. Okay, the same foundation for confidence interval for population variance, confidence interval for population standard deviation. Okay, let's start. Let me do it here. So step 1, the claim, there's no claim. Step 2, hypothesis. Braces, null hypothesis, standard deviation is 4.3. Alternate hypothesis, standard deviation is not 4.3. The sample size is 12. Let me write it here. And part A, if the sample standard deviation is to determined to be 4.8, compute the test statistic. So step 3, test statistic. Chi-squared equals to degree of freedom 11 times sample variance. Now what we are given is sample standard deviation, right? So I need to square it to make it sample variance over population variance. We have population standard deviation here. That's population standard deviation. So we need to square it to make it variance. Okay, now then, let me turn this off. 11 times 4.8 squared divided by 4.3 squared give me 13 something. Step 4, p-value. P-value. We have chi-squared distribution. Okay, now this 4.8 is greater than the claim 4.3, right? So it will be the right tail that I will multiply by 2 later on. Okay, this is 13.70687. Okay, but then I need to double it. Okay, so p-value equals to, because it's two-tailed, right? It's two-tailed here. Sorry, I supposed to have marked it earlier. It's two-tailed. So here I will have 2 times chi-squared CDF, the lower bound 13.70687, upper bound E99, degree of freedom 11. Again, chi-squared CDF is on the distribution list. I get, this is 2 times 0.24964 multiplied by 2. I get 0.49928. Okay, so informal conclusion. The alpha is 0.05 from part B. P-value is strictly much greater than that, so it is failed to reject. Null hypothesis. Okay, notice that in part D, the question, will the researcher reject the null hypothesis? Okay, the answer is no. The researcher will not reject null hypothesis. And why? Because the p-value is greater than alpha. They notice that they do not require us to draw a conclusion. Why? Because we don't even have a claim. Okay, so the conclusion is none. Now the thing is, what are the critical values? What are the critical values? Now you need 5% two-tail means 2.5% each tail. Okay, this is chi-squared critical right. And this one here will be chi-squared critical left. This is inverse chi area to the right, 0.025, degree freedom 11. This is inverse chi area to the right, 0.975, degree freedom 11. Let's see what my calculator tell me. I use handheld calculator, so it will take longer time. This one here is 21.92005. And how about 0.975, degree freedom 11. I get 3.81575. Now notice that my test statistic is in between, right? Which is not on the tail. My test statistic is here. That's 13.7, right? Okay, it's actually quite far from the tail, quite far from either tail. Yeah, it's quite far from either tail. Okay, now unfortunately, this 10.4 hypothesis testing on population variance or population standard deviation has no functions on our calculator to check. Okay, there's no way for us to check that. So you're on your own, basically. There's no way for us to check that. Okay, Now let's deal with the actual problems, the actual word problems. Let's say we do number 11. I try not to get a very long question. Number 11. A piston diameter of a certain hand pump is 0.5 inch. Now, the quality control manager determines that the diameters are normally distributed with mean 0.5 inch and standard deviation 0.004. Now, the machine that controls the piston diameter is recalibrated in an attempt to lower the standard deviation. Okay, so let's say the old machine gives you standard deviation 0.004 and they recalibrate that, and they found out that when they have randomly select 25 pistons from the production line, the standard deviation, the sample standard deviation is now 0.0025. Now, this is clearly less than the standard deviation of the diameter prior to the real calibration. But at the same time, even though the sample standard deviation is less than, it doesn't mean it is consistently less than 0.0025. That's only from 25, a sample of 25 pistons. Okay, now we want to know if the recalibration effective. In other words, is the standard deviation now decreases? Okay, use alpha equals to 0.01. Okay, step 1, the claim. The recalibration was effective. If it was effective, then the population standard deviation after recalibration is less than the previous one. Okay, the population standard deviation after the recalibration is less than the previous standard deviation. Okay, otherwise it's not. Now from here we see this is a left tail. Okay. Now step 3, let me do it here. Step 3, test statistic. Chi-squared equals to degree of freedom times sample standard deviation being squared. Supposed to be sample variance, right? Don't forget to square it to make it variance over population standard deviation that they claim. Don't forget to square it to make it variance. Okay, so 24 times 0.0025 squared divided by 0.004 squared. I get 9.375. Step 4, the p-value. Chi-squared distribution, which is non-negative, skewed to the right continuous curve. Okay, the alpha is 0.01 on the left tail. So this is 0.01. Oh, no. I need to find the p-value, right? So this is 9.375. Now, what is the p-value? The p-value is chi-squared CDF. The lower bound is 0, not from negative infinity, not from negative E99, even though it's actually okay if you do so, but it's supposed to start from 0. okay, up to 9.375, degree of freedom 24. Okay, let me show it to you. Okay, what you're supposed to punch is chi-squared CDF, number 8 here. Number 8 here. Okay, in the lower bound, supposed to be 0. It's not supposed to be negative though, but we do it later. What if you use negative 9.375? Degree of freedom is 24. Okay, 0.00332. 0.00332. Now, suppose I change, instead of 0, I use, let's say, negative infinity. Let's take a look. Okay, you will see the result will be the same. Because the area to the left of the y-axis are actually 0. Right? So suppose I change this to be negative E99. Okay, see that we will get the same result. Okay, so because if you use from negative E99, it will compute the area all the way from negative infinity up to here, which is 0 anyway. Okay, which is 0 anyway. Okay, and then add the area here. So if you use negative E99 here, you will get the same result. Okay, but of course, that's not necessary though. It may make your calculator work a little bit harder. Okay. Now that's the p-value. Step 5. You know what? Let me do step 5 here. Step 5, informal conclusion. Since the p-value is less than alpha, then we reject null hypothesis. Now we reject null hypothesis, yet the claim is with the alternate, right? This is the null hypothesis. We reject that. It means we accept the alternate hypothesis, which is the claim, right? Which is the claim. So apparently from here, the evidence support the claim that at 0.01 significance level, there is sufficient evidence to support the claim. That the recalibration was effective. Now, how about the the test statistic for B, the critical value? The alpha is 1%, left tail. So I need 1% here, 0.01. I need to find chi-squared critical, which is inverse chi, the area to the right 0.99, degree freedom 24. That's inverse chi, the area to the right 0.99, degree of freedom 24. I get 10.85636, and my test statistic is 9.3. This is my test statistic here, which is on the tail region, right? It is on the tail region. That's why we reject null hypothesis. Okay, let's do one more problem and then I move on to the next chapter, chapter 11. You know what? Let me do number 13. Yeah, let me do number 13. Or should I do number 17? I do number 13. Number 13. This was the same question we did from 10.3 on Monday. I think we did number 21 at the time. Okay, now, but they don't give us the statistic anymore. They don't give us the sample standard deviation. They give us the actual sample. Okay, now let's read the question. We did the mean waiting time. Now the managers, starting from the second sentence, the manager is also worried about the variability in waiting times. Prior to the new drive-through system, the standard deviation of wait time was 18 seconds. Now use the data in the following table to decide whether the evidence suggests the standard deviation of wait time is less than 18 seconds now. So that will be our step one, right? Claim. Let me just write it right away. The standard deviation of wait times is less than 18 seconds. Of course, from there, we can build the hypothesis right away. The standard deviation of the wait time is less than 18 seconds. The null hypothesis should be the complement of that. Or our textbook make it sigma is equal to 18. Now step 3, we need to do the test statistic. Then you will see that we still need to find the sample standard deviation, right? Okay, chi-squared equals to degree of freedom. There are 10 data there. It will be 9 times, we don't know, over 18 squared, right? Now let's find out what is the sample variance. Okay, let's find out what is the sample variance. I will do it here. Okay, dn equals to 10. I need to find the sample variance. Okay, now I remember we have that on our calculator. Let's see. I wonder if I still have it. Okay, let me see. Okay, I go to stats, add it. Oh yeah, we still have it. Yeah, we still have it. See the first data 108.5. Remember we did number 21 from 10.3, right? So this is actually in my list 1. So I can calculate, ask the calculator to calculate the one-star statistic from that L1 to give me the sample standard deviation, 15.20504. S equals to 15.20504. Okay. Now, so if you wonder, Thomas, how do you get that, Thomas? Then you go back to my video go back to the recording from Monday, how I plug in the data and how to get these numbers. Okay, you should be able to do it manually also though. Okay, you should be able to do it manually also. Yeah, for you to do it manually, then you need to first find the sum of x and the sum of x squared, which you can find once you plug that into the data. You can see here is sum of x is 780, sum of x squared is here, right? That's 780. Sum of x squared is 62920. 62920.74. Is it right? Uh-huh. Now then, if you want to compute your sample variance, then it will be 10 times 62920.74 minus 780 the squared divided by 10 times 9. Okay, whatever the result you get here, if you apply the square root, then you will get 15.20504. Okay, now let's try it. So it's 10 times 6290.74 minus 780 squared. Now the result should be divided by 90, 10 times 9, right? This is 231.19333. 231.19333. Now apply square root to that. We should get the same result. You see that? Okay. Now, but the number I will use here is sample variance though, not sample standard deviation. So either you use 231.19333, either you use that one, the sample variance, or you can use the sample standard deviation, but don't forget to square it. Don't forget to square it. Okay, so imagine if you already do the square root, but you need to square it back, right? Okay, if you already have rounding error, you do the square root, you round it, and then you square it, you round it again. So instead of doing this, I would just use 231.19333. Okay, well, anyway, I will compute further. Let me go back to this. 9 times 231.19333 divided by 18 squared. That is 6.42204. By the way, from here we see this is a left tail. Why do I need that? Because I need that for my p-value. Which tail to look at? Okay, I have 6.42204, and I need to find the area of that left tail. So p-value is chi-squared CDF. Left bound, lower bound, upper bound, degree of freedom. I get 0.30295. So step 5, but the alpha is 0.05, right? Okay, and the p-value is much larger than that. Informal conclusion. Fail to reject null hypothesis. And finally, we conclude step 6. At alpha equals to 0.05. Is it right? Yeah, 5%, as I remember. There is insufficient evidence to support the claim that the standard deviation of wait time is less than 18 seconds. Okay, now that's for this section. I would like you to try to do number 1 to number, let's say number 1 to number 15. Actually, no need to go from number 1. Maybe start from number 5. Number 5 to number 15. So there are 6 questions to do. Okay, that's all your suggested homework. Okay. Now that's for 10.4. The reason I want to go a bit faster is because of the following. What I plan to do. Okay, what I plan to do. We still have 4 sections to cover. And those 4 sections are from chapter 11. We have hypothesis testing. I think that's 11.1. Hypothesis testing on 2 population proportion. And then we have hypothesis testing on 2 population mean. Now I forget which one is which one. I think 11.2, the 11.2, I think is the dependent case. And 11.3 is the independent case. Now I may happen to switch them. And then after that, the last topic we will do is linear regression. Okay, what I think I want to do is this. On Monday, I will do 2 of this. I think on Monday, I will do 11.1, which is 2 population proportions, and the dependent case. So right now, I will do at least give the foundation for this one here. Okay, now next Wednesday. So today's Wednesday. So today is Wednesday, right? On Monday next week, on the 17th, we will do 11.1 and 11.2. Okay. You know what? Let me check. Is it 11.2 or 11.3? Just to make sure. Just to make sure. Give me a second. I need to look at the book though. Patient with me. I need to see chapter 11. Yeah, that's right. So on Monday, we will do 11.1, 11.2. Now on Wednesday next week, I will do review for test 3. Okay, why? Because the week after that, this is your test 4. You see? Okay, that's your test 4. Okay, now I will do linear regression here, which is not part of your test 4. Okay, I will do linear regression here together with some review. Maybe I do one review first and then we do linear regression, or maybe we do linear regression first, and then do review. But linear regression will be in your final, not in your test 4. Okay, that's why I want to do 11.3 right now. The good news about chapter 11 is they are not building on the top of each other. In other words, I can do 11.3 and then 11.1 and then 11.2 or any order. Okay, now with the time I have left, only half an hour. With the time I have left, only half an hour, I think I can at least give you the foundation. At least the template, right? But I believe you can do more actually. Okay, let's see, 11.3, that's hypothesis testing on 2 population means. We are comparing 2 population means, but we have independent case. Now I will explain further later on the difference between independent case, therefore we'll use this method, and dependent case, which we will see on Monday. So make sure you study this though. Okay, the template. Step 1, the claim, the same. We still have 6 steps, but I want you to see what happened within those 6 steps. Okay, now when it comes to the hypothesis, we have something slightly new here. Instead of comparing that with a constant, you will have mu1 is equal to, less than, equal to, greater, equals to mu2. Okay, now mu1 is not equal to, greater than, less than mu2 for the alternate hypothesis. So you see in the past we have, in chapter 10, we have mu is greater than, let's say 6.7, right? So just you have one parameter compared to a constant. Right now you have 2 parameters comparing to each other. Okay, but once you get that, later on, you need to modify, we need to modify these hypotheses such that the other side becomes a constant. Okay, so we will subtract mu1 minus mu2 is equal to or less than equal to or greater equals to 0. Okay, mu1 minus mu2 is not equals to, greater than, less than 0. We need to modify that. Now, why do we need to modify that, Thomas? Because remember, on the step number 3, let's say here, in step number 3, we always need to have a constant from null hypothesis. Remember that? We need to have constant from null hypothesis. So what constant we will use from the null hypothesis? When we have 2 such thing, well, then you need to modify that to have a constant 0. Okay, now step 3, test statistic. We will use T where we have x1 bar minus x2 bar. The sample mean from two different samples, the means from two different samples, okay, minus mu1 minus mu2. But this guy later on will be our zero over square root of sample variance of the first sample over n1 plus sample variance of the second sample over n2. That's actually the new stuff. If you want to say that's new, that's the new stuff. Okay, if you watch my lecture video, then you will see why the standard error on the denominator looks like that. Has something to do with central limit theorem, has something to do with the addition of two normal distributions. Okay, now in fact, if sigma 1, sigma 2 known, then the test statistic will become Z. Okay, but that's very, very hardly happen. Very, very hardly happen. In fact, even if we know that, we still don't use it. That's what I was told. Okay, basically, if you know the population variance, population standard deviation, you use Z. If you don't know the population variance or population standard deviation, you use T. Okay, you see the substitution, right? Okay, population variance. This, I'm sorry, that was sample variance. This is population variance. This is T. This is Z, standard normal distribution. Okay. Now, how about the p-value? Well, just the same thing. Okay, if you use T, then you look at the T CDF, right? The fact it is left tail or right tail is being seen here. Left tail, right tail, two tail. Oh, nothing really changed other than step 2 and major change in step 3. Okay, the p-value. And then step 5, informal conclusion. Step 6, conclusion. Okay. Now let's see one case from our textbook. Let me use question number 3. Maybe I explain a little bit first about the difference between dependent case and independent case. Independent case like this. Independent case is the situation when you get two samples from two different populations. So let's say you have population of students in Indonesia and population of students in America. You select some of them to take, let's say, some statistic tests, right? And then the results are the following. Okay. Now, what is the difference then? Why do we call that independent? We call that independent because nobody in Indonesian students will be counted here. And nobody from American students will be counted there. That's why we say it's independent. Okay, now, so what is dependent case? Dependent case, you are talking about only one population from which you get a sample. Now then, let's say you have 10 students, and these 10 students will be measured whatever the statistic before and after treatment. Let's say you want to check if a certain vaccine, you want to check if a certain vaccine is effective. Okay, so we measure the antibody before the vaccine, and the antibody after the vaccination. Okay, now you see that the subjects of people, the samples, okay, are the same people. Okay, so let's say Thomas before and after. Okay, the Tim before and after, Ashley before and after. Okay, Stephen before and after, Peter before and after, Esther before and after. Okay, so it's dependent because you have two numbers from the same person before and after, before and after, before and after, before. You can match them. They are dependent. Okay, you can pair them. That's for dependent case. Independent case, no, you cannot pair them. Okay, because the people taking these tests here are exactly totally different people taking these tests here, not the same people. The numbers not coming from the same person. That's why we call them independent case. Okay, now the case that we are dealing here are independent case. Now suppose we have this. So let's go to the cut to the chase. Okay, step one, the claim, there's no claim. Step two, hypothesis. The hypothesis tests whether mu1 is greater than mu2. Oh, okay, so that's the alternate hypothesis, mu1 greater than mu2. Later on, when we modify that to have a constant on one side, that will be mu1 minus mu2 greater than 0. Basically, you subtract by mu2 both sides. How about the the null hypothesis times? Well, just get the complement of that, right? Our textbook will use equal sign, by the way. Okay, so null hypothesis will be mu1 minus mu2 less than equals to 0. Step 3. How about the test statistic? I think I will, once I finish this, then I will just take off. And then on Monday, I will do 1 or 2 more questions from here before we go on to 11.2 and then 11.1. Test statistic, we don't have population standard deviation, so I use T. On the top will be x1 bar 50.2 minus x2 bar 42.0 minus mu1, mu2, minus mu2. That's 0. Okay, it's mu1, mu2, this 0 coming from here. Okay, over square root of sample variance divided by, oops, 6.4 squared divided by sample size plus sample variance divided by the sample size. Now learn to use your calculator. Learn to use your calculator. You should get this number, 50.2 minus 42, that's for the numerator. I get 8.2 divided by square root of 6.2 squared over 25 plus 9.9 squared over 18. You should get this number, 3.08101. Okay, now then, step 4, p-value. That's t-distribution. Okay, that's t-distribution. It's right tail. So 3.08101 right tail. So the p-value will be TCDF, lower bound 3.08101, upper bound E99. Degree of freedom. Oh, for the degree of freedom, choose the smaller degree of freedom. Okay, use smaller degree of freedom. From the first group, the degree of freedom is 24. The second group, the degree of freedom is 17, right? We will use the smaller degree of freedom. Now, this result will be different from the degree of freedom if we use calculator. Okay, I will show you later on how to confirm our answer using calculator, but the result will be off by a little bit. And we have not find the case where the conclusion are different. Okay, so if we want to do it fast, right, then the degree of freedom you use will be the smaller one. Okay, now TCDF, it's on your calculator, 3.08101 up to E99. Degree of freedom, I will use 17. I get 0.00339. What is the alpha, by the way? 10%. Oh, okay. So step 5, the alpha is 10%, right? So informal conclusion, will reject null hypothesis. Step 6, conclusion, none, because we don't even have a claim. Okay. How about critical value? Critical value. You want drug tail 10%. 10% here. You want the T critical, that's inverse T. Area to the left is 90%. We did inverse T when we did 10.3, the critical value. Okay, so nothing new, nothing new. This is, and then degree of freedom, we will use 17. Area to the left is 90%, degree of freedom 17. My calculator will take some time. I get 1.33338. Okay, my test statistic is 3 point something, however. Okay, so the conclusion will still be the same. The conclusion will still be reject null hypothesis. Now, how do we use calculator for this? It will be our calculator to confirm. You will go to stat, test, to sample T test. So you go to stat, test. Now you see two sample t-tests. Okay, we will enter the stats. So let's go back here. Let's see the number. X1 bar is 50.2. Sample standard deviation from the first sample. The first sample standard deviation 6.4. Sample size 25. That's for the first group. The second group, X2 bar is 42.0. Sample standard deviation from the second sample is 9.9. Sample size is 18. We will check mu1 greater than mu2. Okay, is it pull? Say no, we don't pull them. Don't pull them. Under very rare situation, we will pull them. Okay, this is what we get. We pull them if we assume that they come from the same population, okay, which is not the case. Okay, you see that my T's test statistic are the same, right? This is the same test statistic. Okay, now my P value is quite different though. What's the reason? Because they use this degree of freedom while I use 17. They use that degree of freedom. Now, Thomas, why our degree of freedom is different from calculator? The computation for degree of freedom, if you have two samples, is quite complicated. It's quite complicated. It's so complicated such that no teacher actually teach that. Even when we apply that in real life, those mathematicians, those statisticians, they actually just use what I do here. They use smaller degree of freedom. Okay, they use the smaller degree of freedom. So you see that our degree of freedom is different. Okay, that's why our P value also different. Okay, but even though the degree of freedom we use is different, they are different, but the P value also slightly different, but we come up to the same conclusion. See, my P value is less than 10%, right? You see 10% or 5%? 10%. My P value is less than 10%. Their P value also less than 10%. Even if you test this as 1%, my P value will still be reject null hypothesis, and calculator P value will also reject null hypothesis. Okay, so in other words, you can still use calculator here, okay, but it's not a good source for you to check your P value. You can use that to check your test statistic, okay, but not your P value. Okay, your conclusion will still be the same regardless which P value you use from your computation or from calculator. Supposed to be the same. Okay, let me see if I can show you the formula to find degree of freedom from our textbook. Okay, here. This is the formula to find degree of freedom. It's so complicated such that we don't want to do that. This is the formula for degree of freedom. Formula for degree of freedom. But we will not use this formula. Okay, we will not use this formula. We will use the degree of freedom we use will be the smaller, the minimum of the first degree of freedom or the second degree of freedom. Okay, the smaller of either one degree of freedom. Okay, this is where I will end today's lesson. Let me give you some suggested homework. Number 1, number 3, number 5. Yeah, try number 1 to 1, 3, 5. Suggested homework from this 11.3a, number 1, number 3. I did number 3, but I wanted to do it again. And then number 5. Now on Monday, we will continue from this 11.3, do some word problems. Maybe I will spend like 2 questions from 11.3. Then I go on to 11.2 and then 11.1. Okay, that's for today. See you then on Monday.